Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Ulūgh Beg, a name synonymous with astronomical precision, presided over an era of intellectual flourishing centered in Samarkand, a vibrant hub on the Silk Road. His legacy rests upon the construction of an observatory, a monumental undertaking dedicated to the refinement of astronomical knowledge. This endeavor directly addressed a crucial scientific problem of the significant inaccuracies permeating the astronomical tables of the time. Existing models, prominently those articulated in Ptolemy's ***, while foundational, contained discrepancies that hindered accurate predictions of celestial events impacting navigation, calendrical calculations, and the very understanding of the cosmos. Ulūgh Beg's response was a commitment to meticulous observation. He sought to supplant the existing errors with a new level of precision. The Samarkand Observatory, built in the early 15th century, was more than a collection of instruments. It was a dedicated research institution, a place where the cosmos itself was interrogated through rigorous measurement. The core methodology involved the painstaking observation of celestial bodies, employing instruments of unprecedented scale and accuracy. The cornerstone of this enterprise was a giant sextant, a remarkable device that allowed for the precise measurement of angles between celestial objects. This instrument, a testament to the ingenuity of the time, enabled Ulūgh Beg and his team to chart the heavens with a degree of accuracy previously unattainable. The fruit of their labor was the celebrated Zij-i Sultani or the royal tables. These tables, meticulously compiled over years of observation, provided detailed information on the positions of stars and planets. The Zij-i Sultani surpassed the accuracy of any previous astronomical work. It offered a new standard for understanding the movements of celestial bodies. It corrected numerous errors present in earlier tables, significantly improving the precision with which astronomers could predict the positions of planets and stars. These tables provided the data needed for accurate astronomical calculations and facilitated a deeper comprehension of the cosmos. The need for such precise measurements was acute. Astronomical knowledge at the time, while advanced, was still limited by the observational techniques available. Existing data, based on the observations of earlier astronomers, particularly those from the Hellenistic period, had inherent limitations. The instruments were less precise, and the accumulation of errors over time had led to significant discrepancies. Ulūgh Beg recognized these shortcomings and sought to rectify them through direct, painstaking observation. Ulūgh Beg's work was deeply rooted in the intellectual traditions of Islamic astronomy. He built upon the foundations laid by earlier scholars, drawing inspiration from their advancements in mathematics and observational techniques. The legacy of figures like Al-Khwarizmi, whose work on algebra and algorithms had revolutionized mathematical thought, provided the essential tools for astronomical calculations. The development of trigonometric tables, essential for converting angular measurements into usable data, was another critical contribution of Islamic scholars that paved the way for Ulūgh Beg's achievements. Trigonometry, a branch of mathematics dealing with relationships between the sides and angles of triangles, was crucial to the accurate determination of celestial positions. The Zij-i Sultani quickly became a standard reference for astronomers across the Islamic world and beyond. Its influence resonated for centuries, guiding astronomical calculations and shaping the understanding of the cosmos. The tables offered a remarkably accurate depiction of the heavens. They provided a crucial framework for navigation, enabling sailors to chart their courses with greater precision. Furthermore, they informed the development of calendar systems, which were vital for religious observances and the organization of daily life. The enduring relevance of Ulūgh Beg's work is undeniable. Accurate astronomical data remains fundamental to our understanding of the universe. Modern navigation systems, such as GPS, rely on precise knowledge of the positions of satellites, which are in turn dependent on accurate astronomical models. The study of cosmology, the origin and evolution of the universe, also relies on the data derived from astronomical observations. Ulūgh Beg's quest for precision continues to inspire and inform scientific inquiry. His commitment to rigorous observation, his dedication to mathematical accuracy, and his unwavering pursuit of knowledge have left an indelible mark on the history of science. The Samarkand Observatory, a physical embodiment of his intellectual ambition, stands as a monument to the power of observation and the enduring human desire to understand the universe. The pursuit of celestial precision at Samarkand demanded instruments of unprecedented scale and accuracy. These were the tools with which Ulūgh Beg and his team tackled the intricate problems of the cosmos. Their primary objective was to surpass the observational limitations of previous eras, refining the positions of stars, mapping planetary movements with greater fidelity, and determining the length of the sidereal year with unparalleled exactness. The challenges were formidable, requiring not only advanced mathematical understanding, but also ingenuity in engineering and construction. At the heart of the Samarkand Observatory's capabilities lay the giant sextant, an instrument of monumental proportions. This was a portable device. It was an integral part of the observatory's structure, built directly into the bedrock. Its arc, the graduated scale used for measuring angles, was constructed of carefully selected materials, ensuring stability and minimizing the effects of thermal expansion and contraction. The radius of this sextant was substantial, allowing for exceptionally precise measurements. The larger the radius, the smaller the angular error inherent in the readings. This architectural integration was a deliberate design choice, emphasizing the observatory's commitment to accuracy. The sextant's size and fixed position allowed for a level of stability that smaller, more mobile instruments could never achieve. The construction and use of this immense sextant were themselves feats of engineering. The arc was meticulously calibrated, likely employing a combination of astronomical observations and geometric calculations to ensure accurate division into degrees and minutes. The sighting mechanism, the part used to visually align with celestial objects, would have required careful design to minimize parallax errors, the apparent shift in position caused by the observer's viewpoint. These instruments, along with other specialized tools, facilitated the precise measurement of celestial angles. Beyond the giant sextant, the observatory housed other instruments designed to address specific observational needs. These included quadrants, used for measuring altitudes, and armillary spheres, which provided a physical model of the celestial sphere, allowing for the visualization of planetary movements. Each instrument was crafted and calibrated with the same meticulous attention to detail that characterized the entire enterprise. The creation of these tools, and the meticulous care with which they were employed, represent a significant advance in observational astronomy. Ulūgh Beg and his team employed these instruments to gather a wealth of astronomical data. They observed the positions of stars, charting their coordinates with unprecedented precision, and meticulously tracked the movements of the planets, recording their longitudes and latitudes at regular intervals. And, perhaps most famously, they determined the length of the sidereal year, the time it takes for the Earth to complete one orbit around the Sun, with remarkable accuracy. A tangible example of their work is the determination of the sidereal year. Ulūgh Beg's value of 365 days, 6 hours, 10 minutes, and 18 seconds is extraordinarily close to modern measurements. This remarkable precision, achieved centuries ago, demonstrates the power of their observational techniques and the quality of their instruments. Its value, differing from the modern accepted value by a mere fraction of a second, is a testament to the dedication and skill of the Samarkand astronomers. Comparing Ulūgh Beg's observations to those of Ptolemy, the most influential astronomer of antiquity, reveals the dramatic improvement achieved. Ptolemy's observations, while groundbreaking for their time, were limited by the instruments available and the observational techniques employed. Ulūgh Beg's measurements, made with larger and more precise instruments, offered a significant refinement of Ptolemaic data. For example, Ulūgh Beg's star catalogs, compiled from painstaking observations, provided more accurate positions than those found in Ptolemy's Almagest **. The calculations underpinning these observations relied heavily on the principles of spherical trigonometry. This branch of mathematics, dealing with the relationships between angles and sides of spherical triangles, was indispensable for converting angular measurements into celestial coordinates. Ulūgh Beg and his team utilized trigonometric functions, such as sine, cosine, and tangent, to solve complex geometric problems related to the positions of celestial objects. They employed formulas like the sine rule and cosine rule for spherical triangles to calculate distances and angles on the celestial sphere. These calculations allowed them to translate the raw data gathered from their observations into a usable form, creating the precise star catalogs and planetary tables for which they are renowned. The intellectual landscape of Ulūgh Beg's time profoundly shaped his scientific endeavors. A direct influence on Ulūgh Beg's work was the legacy of Islamic astronomy, which had already made significant strides in observational techniques and mathematical frameworks. The contributions of Nasir al-Din al-Tusi, a 13th century Persian polymath, are particularly noteworthy. Al-Tusi's development of the Tusi couple, a geometrical construction that provided a mechanism for representing linear motion using circular motion, found its way into the astronomical models of the Samarkand school. This geometrical innovation, along with the advancements in observational practices championed by Al-Tusi, provided a foundation upon which Ulūgh Beg built his astronomical program. The influence of Al-Tusi is evident in the sophistication of the mathematical models used at the Samarkand observatory. The impact of Ulūgh Beg's astronomical work extended far beyond the walls of his observatory. His precise observations and meticulously compiled data exerted a direct influence on subsequent generations of astronomers. One of the most significant examples of this influence is seen in the work of Tycho Brahe, the Danish astronomer, whose own highly accurate observations of the late 16th century revolutionized astronomy. For his detailed measurements of planetary positions, which served as the foundation for Johannes Kepler's laws of planetary motion, were, in part, made possible by the precedent set by Ulūgh Beg and the Samarkand astronomers. For his meticulous approach to observation, his emphasis on precision, and his dedication to gathering comprehensive data, all mirrored the ethos of the Samarkand school. Brahe's work, fueled by the accurate data of Ulūgh Beg, would ultimately lead to the development of more accurate astronomical models in Europe. The legacy of Ulūgh Beg's observatory lies not only in its specific astronomical findings, but also in its enduring influence on the development of scientific methodology. The emphasis on rigorous observation, the meticulous attention to detail, and the commitment to mathematical accuracy all became hallmarks of the scientific enterprise. The Samarkand Observatory, a testament to the power of human curiosity and the pursuit of knowledge, continues to inspire. Ulūgh Beg's most ambitious undertaking, a project that would cement his place in the annals of scientific history, was the compilation of the Zij-i Sultani or the Royal Tables. This monumental work, completed around 1437, represented the culmination of decades of meticulous astronomical observation and sophisticated mathematical calculation. The Zij, a comprehensive astronomical handbook, sought to address a fundamental set of problems, providing accurate tables for the positions of celestial bodies, including the sun, moon, and planets, alongside the positions of fixed stars. These tables were essential for a wide range of applications, from calendrical calculations and astrological predictions to navigation and religious observances. The structure and organization of the Zij-i Sultani reveal a clear intellectual lineage, reflecting the influence of earlier astronomical traditions. The most significant predecessor, Ptolemy's Almagest served as a foundational text. Ulūgh Beg adopted a similar framework, organizing the tables and calculations in a systematic manner. However, the Zij also demonstrated significant departures from Ptolemy's model. Ulūgh Beg and his team, for example, incorporated more recent observations and refinements, leading to more accurate positions for celestial objects. They expanded upon Ptolemy's star catalog, including a much larger number of stars and providing more precise coordinates. The Zij-i Sultani is a rich compendium of astronomical data and mathematical methods. It commenced with tables of star positions, meticulously detailing the celestial coordinates of over 1,000 stars. These coordinates, expressed in terms of celestial longitude and latitude, were determined through years of painstaking observations. The tables provided the foundation for understanding the positions of stars at any given time. The Zij next provided detailed planetary longitudes and latitudes, calculated using sophisticated mathematical models. These models, based on the geocentric theory prevalent at the time, allowed astronomers to predict the future positions of the planets with a high degree of accuracy. The work also contained extensive trigonometric tables, essential for solving astronomical problems. These tables, which detailed the values of trigonometric functions such as sines, cosines, and tangents, were crucial for converting between different coordinate systems and for calculating the distances and relative positions of celestial objects. The methodologies employed in the creation of the Zij were a testament to the sophisticated mathematical and observational skills of the Samarkand astronomers. Spherical trigonometry, the branch of mathematics concerned with the relationships between angles and sides of spherical triangles, played a central role. This allowed the astronomers to accurately calculate the positions of celestial objects on the celestial sphere. Interpolation techniques were also crucial. These methods, which involved estimating values between known data points, were essential for creating smooth and accurate tables. The Samarkand astronomers skillfully employed interpolation to refine the values of astronomical parameters and to generate tables that were both precise and easy to use. The compilation of the Zij depended on the careful collection and analysis of observational data. The astronomers meticulously recorded the positions of celestial objects using the instruments of the observatory. These observations, which spanned many years, provided the raw data that formed the basis of the tables. Consider, for instance, the star catalog included within the Zij-i Ulūgh Beg's catalog improved on Ptolemy's, more than doubling the number of stars included. Each star was assigned a precise celestial longitude and latitude, a testament to the accuracy of the Samarkand observations. The catalog also included the star's magnitude, a measure of its brightness, and its position relative to the constellations. These details, recorded with unprecedented precision, provided a comprehensive map of the night sky. Moreover, the Zij provided detailed planetary tables. These tables allowed astronomers to predict the positions of the planets with remarkable accuracy. The Zij provided tables for the Sun, Moon, and the 5 known planets Mercury, Venus, Mars, Jupiter, and Saturn. The tables enabled astronomers to calculate the positions of the planets at any given time, allowing them to determine their longitudes, latitudes, and other orbital parameters. The Zij-i Sultani possessed a profound and lasting impact on the development of astronomy, both in the Islamic world and in Europe. It became a standard reference for astronomers for centuries. Its influence can be seen in the work of many later astronomers, including those who contributed to the scientific revolution. In the Islamic world, the Zij served as a model for subsequent astronomical tables. Astronomers in various regions adopted the Zij methods and incorporated its data into their own works. This facilitated the continued advancement of astronomical knowledge and the dissemination of accurate astronomical data. The Zij-i Sultani directly influenced the development of astronomical tables in Europe. The tables' accuracy and comprehensiveness made them a valuable resource for European astronomers who were beginning to challenge the established Ptolemaic system. The Zij data served as a crucial source of information for astronomers such as Nicolaus Copernicus, who used the tables to refine his own astronomical models. Copernicus, in his groundbreaking work De Revolutionibus Orbium Celestium, relied on the Zij data to support his heliocentric model of the solar system. The Zij influence extended to Johannes Kepler, who, in his pursuit of the laws of planetary motion, also consulted the Samarkand tables. The Zij precise data on planetary positions provided Kepler with essential information for his calculations. Furthermore, the Zij-i Sultani fostered the development of astronomy in the Islamic world. It formalized the practice of astronomical observation and calculation, establishing a legacy of precision and mathematical rigor. The Zij-i's impact extended beyond astronomy, influencing the development of mathematics, geography, and other scientific disciplines. Ulūgh Beg's work, along with the contributions of other Islamic scholars, helped to preserve and advance the scientific knowledge of the ancient world. The Zij-i Sultani represents a pivotal achievement in the history of astronomy. It embodies the spirit of scientific inquiry, the pursuit of accurate observation, and the application of sophisticated mathematical methods. The Zij-i's legacy, as a source of astronomical data and a model for scientific practice, continues to resonate. Its influence on subsequent astronomers, both in the Islamic world and in Europe, is undeniable. The Zij-i Sultani stands as a testament to the enduring power of human curiosity and the relentless pursuit of knowledge. Ulūgh Beg's profound impact extends beyond the realm of observational astronomy. He was a formidable mathematician whose contributions were essential for the advancement of his astronomical endeavors. Accurate astronomical calculations hinge upon precise trigonometric values, and Ulūgh Beg recognized the critical role of mathematics in refining the Zij-i Sultani. His work in trigonometry and spherical geometry provided the foundation for the unprecedented accuracy achieved in his celestial observations. The primary challenge addressed by Ulūgh Beg's mathematical work was a necessity for highly accurate trigonometric tables. Earlier astronomical works, while significant, often relied on tables with limitations in precision. These inaccuracies, although minor, could accumulate and significantly impact the accuracy of astronomical predictions. Ulūgh Beg sought to overcome these limitations by developing trigonometric tables of unparalleled precision for the time. He meticulously calculated values for sine, cosine, and tangent functions, utilizing advanced computational techniques. Ulūgh Beg's methodologies were rooted in the established mathematical knowledge of his era, drawing heavily upon the works of his predecessors, particularly the Islamic mathematicians who had significantly advanced trigonometry. His work demonstrably built upon the foundations laid by figures such as Al-Khwarizmi, whose contributions to algebra provided essential tools for solving trigonometric problems. Furthermore, he was influenced by Nasir al-Din al-Tusi, whose work on spherical trigonometry, particularly his treatise on the quadrilateral provided crucial methods for solving spherical triangles. Ulūgh Beg adopted and refined these techniques, adapting them to the specific needs of astronomical calculations. He also incorporated the advancements in decimal notation, which facilitated more precise calculations compared to the cumbersome sexagesimal system that was still widely used. Specific examples of Ulūgh Beg's trigonometric calculations are readily available in the Zij-i Sultani. The tables contained Within the asterisk, Zij provided precise values for trigonometric functions at small intervals, allowing for accurate interpolation. For instance, he calculated the sine of 1 degree to a high degree of accuracy, a feat that required immense diligence and sophisticated computational methods. These precise values were then applied to calculate the positions of celestial bodies, predict eclipses, and construct astronomical models. The Zij included detailed tables of sines, tangents, and cotangents, meticulously computed to several decimal places. The level of accuracy achieved by Ulūgh Beg was a significant leap forward. The comparison of Ulūgh Beg's trigonometric tables with those of earlier astronomers reveals the advancements he made. Prior to Ulūgh Beg, astronomers often worked with tables that were based on the Ptolemaic system, relying on calculations that were less precise. Ulūgh Beg's tables, by contrast, provided data of far greater accuracy, allowing for more reliable astronomical predictions. The improved accuracy was especially crucial for calculating the positions of the sun, moon, and planets, which were essential for establishing calendars, predicting eclipses, and navigating the celestial sphere. Ulūgh Beg's mastery extended beyond plain trigonometry to the more complex field of spherical geometry. Spherical geometry is essential for solving astronomical problems. It deals with the geometry of the sphere and allows astronomers to accurately determine the positions of celestial objects as they appear on the celestial sphere. He developed and employed methods for solving spherical triangles, which are fundamental to understanding the relationships between celestial objects. The ability to solve spherical triangles enabled him to compute the distances between stars, determine the coordinates of celestial objects, and model the movements of planets. This was integral to his astronomical work. The significance of Ulūgh Beg's work in spherical geometry lies in its direct application to astronomical problems. His methods allowed him to relate the positions of stars and planets to the observer's location on Earth. This was critical for constructing accurate star charts, determining the obliquity of the ecliptic, the angle between the plane of Earth's orbit and its equator, and calculating the precession of the equinoxes, the slow westward movement of the equinoctial points along the ecliptic. These calculations were essential for the accuracy of the asterisk Zij-i Sultani asterisk. The influence of Ulūgh Beg's mathematical contributions extended across generations. His work served as a model of precision and rigor for subsequent astronomers and mathematicians. His trigonometric tables, for example, were utilized for centuries. They provided a standard of accuracy that influenced the development of astronomical tables in various cultures, including those in Europe. The direct influence of Ulūgh Beg's mathematical work can be seen in the contributions of later astronomers and mathematicians. For instance, the work of the Ottoman astronomer Taqi al-Din Muhammad ibn Maruf, who lived in the 16th century, demonstrated a clear understanding of and appreciation for Ulūgh Beg's precision. The Ottoman astronomer's own astronomical tables, while incorporating his own observations, were built on the foundation of the methods and techniques that Ulūgh Beg had pioneered. The emphasis on accuracy and the use of sophisticated mathematical tools, evident in Taqi al-Din's work, can be traced directly to Ulūgh Beg's legacy. Similarly, the Persian astronomer and mathematician Ghiyath al-Din Jamshid al-Kashi, who lived before Ulūgh Beg, influenced the development of computational techniques used by him. Ulūgh Beg built upon this foundation to achieve greater accuracy. Ulūgh Beg's contributions to mathematics, particularly his work in trigonometry and spherical geometry, were pivotal for the advancement of astronomy. His meticulous calculations, combined with his sophisticated methods, allowed him to achieve unprecedented accuracy in his astronomical observations. He not only advanced the practice of astronomy, but also significantly contributed to mathematical knowledge. His work, which drew upon the intellectual heritage of earlier Islamic scholars, was, in turn, a source of inspiration and a model for future generations of astronomers and mathematicians. Ulūgh Beg's enduring legacy resides in his profound integration of observational rigor and mathematical precision. His work, much like a finely crafted instrument, combined the finest materials, the most advanced mathematical techniques of his time, with the keenest observational skills. This synthesis produced results that far surpassed the existing standards, setting a new benchmark for astronomical inquiry. The pursuit of accuracy, a hallmark of his scientific endeavors, was not a solitary goal. It was inextricably linked to his mathematical prowess. His capacity to apply advanced trigonometric methods, for instance, was essential for interpreting the data gathered from the observatory. The meticulousness he brought to his calculations, fueled by the work of earlier scholars like al-Kashi, was critical for achieving the precision that defined his astronomical tables. The impact of Ulūgh Beg's endeavors extended beyond the immediate realm of astronomy. His work served as a bridge, connecting the mathematical achievements of earlier Islamic scholars with the astronomical practices of his own time. The asterisk Zij-i Sultani asterisk, the astronomical handbook produced by his team, became a vital resource for astronomers across the Islamic world and beyond. It was a testament to the power of combining precise observations with sophisticated mathematical models. The very structure of the asterisk Zij asterisk, its detailed tables, and the accompanying explanations provided a template for future astronomical works. This influence is readily apparent in the work of later astronomers who built upon his methods, further refining and extending his achievements. The significance of Ulūgh Beg's work is further illuminated when considered within the broader context of the Islamic Golden Age. This period, marked by a flourishing of intellectual and scientific activity, witnessed a remarkable exchange of knowledge between different cultures. Scholars translated and preserved the works of the ancient Greeks and Romans, while also making original contributions in various fields, including mathematics, astronomy, medicine, and philosophy. Ulūgh Beg's observatory and his scientific output stand as a powerful symbol of this era. His dedication to scientific inquiry, his patronage of scholars, and his commitment to the pursuit of knowledge reflect the spirit of intellectual curiosity that characterized the Golden Age. The challenges Ulūgh Beg faced were considerable. He operated within a complex political landscape, a realm where scientific pursuits could be subject to the whims of rulers and the constraints of societal norms. The very act of building an observatory and assembling a team of scholars required considerable resources and political acumen. It was a testament to his vision and determination that he was able to overcome these obstacles and to establish a center of scientific excellence. The fact that his work survived, despite the political turmoil that ultimately led to his demise, speaks to its enduring value. Ulūgh Beg's legacy is not simply that of a skilled astronomer. He was a visionary who understood the importance of combining observation with mathematical rigor. He was a leader who fostered collaboration and encouraged the pursuit of knowledge. His observatory at Samarkand, a monumental achievement in itself, became a beacon of scientific learning. His work continues to inspire the pursuit of accuracy, the use of sophisticated mathematical tools, and the emphasis on empirical observation, all hallmarks of his approach, remain central to the scientific endeavor today. Consider Taqi al-Din Muhammad ibn Maruf, a 16th century Ottoman polymath. The precision he brought to his astronomical work, the detailed observations, and the sophisticated mathematical models he employed directly reflected the influence of Ulūgh Beg and his legacy. Taqi al-Din's observatory in Istanbul, although short-lived, exemplified the continued commitment to astronomical inquiry that Ulūgh Beg's work had inspired. Taqi al-Din, in turn, contributed to the development of astronomical instruments. His book, the Book of the Light of the End of the Heavens, demonstrated the continued emphasis on observational accuracy and the use of advanced mathematical techniques, a direct inheritance from Ulūgh Beg's approach. The impact of Ulūgh Beg's work extends beyond the realm of astronomy. His approach to scientific inquiry, which emphasized the importance of combining observation with mathematical rigor, has had a lasting influence on the development of science. The emphasis on accuracy, the use of sophisticated tools, and the commitment to empirical observation, all hallmarks of his approach, remain central to the scientific endeavor today. The meticulousness he applied to his work, the careful measurements, and the detailed calculations established a new standard for scientific practice. The enduring value of Ulūgh Beg's work lies in its blend of scientific achievement and intellectual vision. He was not only a brilliant astronomer, he was also a patron of learning, a leader who inspired others, and a man who understood the importance of scientific inquiry. His legacy continues to resonate. His achievements remind us of the power of human curiosity, the importance of collaboration, and the enduring value of knowledge. He stands as a testament to the capacity of human beings to push the boundaries of understanding, to challenge conventional wisdom, and to leave a lasting mark on the world. The story of Ulūgh Beg, therefore, is more than a historical account. It is an enduring inspiration for anyone who seeks to understand the universe. In the vast expanse of scientific history, Ulūgh Beg's name shines brightly, a testament to the power of rigorous observation and mathematical precision.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.